Yep. All right, Charji, thanks so much for the introduction. It's a pleasure to speak here. Thanks for coming. I'll be talking about work called Retiring Adult, New Datasets for Fair Machine Learning, and this joint work with Francis Ding, John Miller, and Ludwig Schmidt. So this talk is about datasets in machine learning. And it's something that I've always found fascinating about machine learning, that we're actually using datasets differently from other sciences and especially the social sciences. We primarily use datasets as benchmarks. So we kind of split data into training and testing sets, and we sort of agree that we can do whatever we want on the training set. You can throw the kitchen sink at the training set, but when it comes to the test sets, we need to be sort of careful, and we evaluate and compare methods on the test set and rank them and find out what works best and improve on it and so forth. So this is kind of the usual workflow in machine learning that we take for granted at this point. It's become so common that it's kind of like something we no longer question. And it's fueled many advances in the area or the field that you all know about, ImageNet and other things. The deep learning revolution is sort of tied to data sets in a significant way. And it's easy to sort of overlook that this is actually a fairly recent practice. And so this practice of data sets as benchmarks kind of emerged in the 1980s. It was, something that became mainstream in the 80s. And Pat Langley wrote a sort of retrospective on machine learning in 2011, where he said that this experimental movement was aided by another development. David Aha, then a PhD student at UCI, began to collect data sets for use in empirical studies of machine learning. This grew into the UCI Machine Learning Repository, which he made available to the community by FTP in 1987. This was rapidly adopted by many researchers because it was easy to use and because it let them compare their results to previous findings on the same task. Okay, so this is kind of how this came about. The internet started, people had like access to the internet, at least in North America, for data sharing. And so people began organizing and collecting data sets. And this repository here, I'm sure many of you have seen. It's the UCI Machine Learning Repository. It hosts a number of data sets. And here are the most popular data sets in the UCI Machine Learning Repository to date. And the first one is associated with Fisher's 1936 article. It's very small, 50 instances, 3 features, something like that. It's the famous IRIS data set. Then number 3, 4, and 5, something about wine and heart disease. I don't actually know exactly what these data sets are about, but they're on there. And the second data set is the unlikely protagonist of the story I'm going to tell you in this talk, due to its somewhat surprising impact on the fairness in machine learning community that it has had. Okay, so what is this adult data set? It's, census data at the outset, at least that's what it says. And it's about 50,000 instances with 14 features. So it's tabular data. It's like just a big table. It was donated in 96. And it's been used many times since then. And so if you look at the description, it's very glib. It just says, extraction was done by Barry Becker from the 1994 census database, according to some criteria, who knows what, age, AGI, some other things, and so forth. And the prediction task is determine whether a person makes over $50,000 a year or not, okay? So this is the entire description. And it says you can email ronniek@life.com for questions, okay? So more on that later. We might actually be emailing ronniek@life.com in a little moment. Okay, so 1994, by the way, was an amazing year, also a sad year in some ways. But apparently Americans used to drink Crystal Pepsi, and they paid about $1 per gallon of gas, and the internet was new. You would log on to America Online using your Windows 3.11 box. So 1994 is like a long time ago, okay? It's is my point here, right? Things were a little bit different in 94, and that's something to keep in mind about this data sets. It's pretty old. The data is pretty old. And so let's look at the attributes a little bit. Again, the target variable is whether you make more or less than $50,000, dollars. And I'm just copy and pasting the description here, you don't have to parse this. It just gives you an impression of like, what's all the information that we kind of have about this data set. It has some features like age, worker class, some sampling weight, education, something else about education, marital status, occupation, relationship. And then it has notably, and this became important for fairness research, an encoding of race, here encoded as white, Asian Pacific Islander, American Indian Eskimo, other and black. These are, of course, no longer used in this form by the Census Bureau today. Sex is available, encoded binary as female, male. There's a capital gain, capital loss attribute, and some other stuff, and native country, okay? And so here's what happened. At some point in 2009, the first papers on fairness in machine learning started using UCI Adult, okay? And so the papers that started doing this were, some of the earliest papers on algorithmic fairness, which today you might not necessarily know about, but they were influential. And this was work by Toon Kulders and collaborators who basically tried to satisfy, build machine learning predictors while satisfying some kind of independence constraint, which says that your predictor or your prediction should be statistically independent of some sensitive attribute like race or sex, okay? And so they wanted to experiment with this, and this is where UCI Adult came in, okay? There is also, I should note, an even earlier paper by Podresky, Ruggieri, and Turini that was also one of the first algorithmic fairness papers, and that used an even older UCI dataset called the German credit dataset, which didn't catch on in the same way. Okay, so I asked Toon Kulders, like, why did you start using this? And he gave a very thoughtful answer that is enlightening. He said, well, the main interest of picking this data set at the time were the presence of a sensitive attribute, gender. The base rates for males and females are different. What he means by that is the income levels of men and women in the United States in 1994 were, of course, different, still are. The label itself can be considered ground truth. And he elaborates on that. What he means by that is there's, of course, structural discrimination reflected in the income distribution or the income levels of men and women. However, at least the Census Bureau did like a good effort trying to collect the income accurately and reliably, okay? So, and I think this is this showed a lot of foresight, and this was, a good reasoning that he had back then. And so it's actually, remarkable. But and then sort of it took on as it goes in machine learning, right? So here's fairness didn't immediately take off, as many of you know. It had sort of these malaise years where it was around, but people didn't really care too much about this topic in computer science. And between 2011 and 2016, there were only like a couple of handful of papers on the topic. But then when 2016 came and fairness became a sort of major research area within computer science, so did sort of the use of UCI Adult became, or become like more and more, significant. Okay, so here in 2017, there are already like quite a few papers. 2018, even more. 2019, suddenly like lots and lots of papers were using UCI Adult. And 2020, even more. And I have to do another slide soon for 2021. But my point is that there are a huge number of papers in this area using UCI Adult. For all sorts of different things, okay? Building fair predictors, so predictors that satisfy some kind of fairness constraint, evaluating causal fairness criteria, privacy and fairness trade-offs, software tools that, implement these methods, and so forth, okay? Fair representation learning. So there is all sorts of stuff, being done on this one data set, UCI Adult, okay? And so we did a quick count, and we can find at least 300 papers on algorithmic fairness that use UCI Adult as a benchmark data set, okay? By the way, for those of you who just joined, I'm monitoring the chat window on a second screen. So if you wanna, interject with a question, feel free to drop that in the chat and I can get to it, okay? So, somewhat unexpectedly, this data set just ended up having a huge amount of impact on the algorithmic fairness community, even though at the outset, we know very little about this data set, okay? So this is kind of interesting because the fairness community has recognized the importance of data sets, okay? We know that data sets decide framing and problem formulation, so they sort of point, they formalize what we're doing, they sort out who is represented and how, They organize communities, they prioritize research directions, they represent labor practices and how the data was collected and so forth. So data sets are pivotal and central to machine learning research. And so this has motivated some data set innovations, mostly in cognitive domains like vision and text and so on, but much less so in tabular data. So when it comes to tabular data, most papers in this area use just a few data sets and achieve among them UCI Adult. So it's basically all we rely on. And I want to sort of emphasize that many decision-making processes where fairness concerns arise actually are based on tabular data. They're not necessarily based on images or something, right? Think about criminal risk assessment, credit scoring and lending, social services, all sorts of bureaucratic processes where machine learning or statistics may be used, often actually work from plain old tabular data. And here we really have basically only one benchmark data set. So what I'm going to do in this talk is, offer some kind of archaeology of the UCI Adult data set. So we're going to look at where it came from, its influence and its issues that limit sort of its external validity and why it's on its own not a good benchmark. And so we're going to, I'll tell you about a new software package that we created, which creates new data sets from US Census data sources, and maybe a slightly more principled way and also a more diverse set of data sources. And I'm going to tell you new findings, or going to show you findings on these new data sets that, in my opinion, challenge some of the existing narratives in, algorithmic fairness. Okay, so what do I mean by archaeology? This is, I love this quote by philosopher of science, Ian Hacking, who wrote that archaeology organizes the past to understand the present. It lifts the dust cover off a world that we take for granted. It makes us reconsider what we experience as inevitable. Okay, so archaeology is sort of a research methodology by which we can, look at things that have happened and reconstruct how they happened, and in doing so, understand where we are at today. Okay, so I want to do that for a UCI Adult, and I'll tell you a little bit to understand that, give you some context, tell you about US Census data products. What is it actually that the Census Bureau releases, and what is it based on? That's kind of the first step, because we know UCI Adult is based on US Census data. We know the US Census Bureau mostly for the census, the count, that happens every 10 years and takes stock of the population of the United States. But actually, the US Census Bureau also offers several high-quality data products that are extremely important for social research and are used by many scientists around the country. And they're based on extensive annual surveying efforts, and several of them are publicly available and you can use them, okay? Some are aggregate statistics and tables, but also others are microdata samples. So others are about, actually individual rows and, features about individuals. The largest surveying effort of the Census Bureau is the American Community Survey. Gives you sort of comprehensive social, economic, and housing data at many levels of geography, even smaller communities. It's a very important household survey, and it's a mandatory annual survey. It's actually, mandated by law that when you get the invitation for the survey, you fill it out, okay? So it's mailed out to approximately 3.5 million households each year. Because it's mandatory, it has a pretty high response rate, so it has excellent coverage. It's about 70% of the responses, or 70% of these households respond. And that's, the survey gets released as a public use microdata sample each year. So each year the Census Bureau prepares some kind of release from this survey, which has individual rows, okay? There's another important survey that became, relevant in the pandemic, especially. It's the current population survey. It's non-mandatory, it's monthly phone or in-person survey. It's much fewer households, but it gives you more information. Okay, it's sort of, especially on economic things, it gives you more detailed information. And it's used, for instance, when you look at unemployment numbers each month. This is based on CBS data. Okay, so the unemployment numbers you saw during the pandemic, as they rise and fell, they were based on CPS. Again, there's some notable differences between these two things that I'm not going to get into. Okay, So we tried to figure out where does this UCI adult data set actually come from? Okay, so is it, ACS or the CPS or something else entirely? And it's not exactly clear from the feature because everything has sort of, all the names have changed since then, all the encodings have changed since then. It's not exactly clear where you should even be looking for that. But we managed to match all these 48,000 records from the UCI adult data set uniquely to some census data eventually. And the source actually turns out to be the 1994 CPS, and specifically the annual supplement to the CPS, which is still available from a service called iPumps. And so this is where we look. And we match these things based on different heuristics. The names weren't the same, so we had to look at the features sort of and figure out what's corresponding to each other in these data sets. Some countries in this IPUM source are coded as unknown in UCI adult, so we had to do some sort of matching there. But eventually we found it all, except for this one column, which is called AFNLWGT and UCI adult. It's probably a sampling weight that was used at the time. So we did email Ronnie K at life.com 25 years after he contributed this data set. I did not expect to get an email, but actually he replied more or less immediately. And unfortunately, he didn't have more information on, a final weight. It's probably gone. So we weren't able to recover this one. It will be missed. But it's not so bad because there are many other sampling weights available, and they're probably replace this column later on. Okay, but there are many others. And arguably, sampling weight shouldn't be used for prediction anyway. So it's a little bit weird the sampling weight is even in UCI adult. Okay, but I say arguably because my friend Eric Price actually did argue with me on that. So maybe it should be used for prediction. I don't know. What are some good aspects of UCI adult? Things I like about this data set, especially relative to other machine learning data sets that we often use. It's based on established survey and data collection standards by the Census Bureau. It comes from a quality sampling frame capturing the US population. The Census Bureau has lots of experience with these things. Involves skilled and compensated labor that's better than sort of ad hoc MTurk collection that we often do in machine learning. And it's thoroughly documented. You can go to Census Bureau and actually get a ton of information about it. Okay, and arguably census data avoids some known issues that were raised with machine learning benchmarks in other domains. So that's good. But there are some significant issues, right? Which is kind of, what we're trying to address, right? So first of all, it's very old. 1994, a long time ago. And in particular, the census encodings for race have changed substantially since then, which is relevant for fairness research. State information was not included in the, UCI adult release, as were many other features, that are available in census, but not in UCI adult. So there's a lot more. And it's fair to say that this really underutilizes the wealth of census data that's available. So why limit ourselves to UCI adult? But also, and this is a pretty sort of significant technical issue, the $50,000 threshold in the target variable for income is actually really high. Okay, so in 1994, that was the 76th percentile of individual income in the United States, and the 88th among the Black population, and the 89th percentile among women. Okay, so it's a very sort of extreme, threshold for income. So you're not really predicting whether or not somebody's above or below median income. You're predicting whether they have sort of high income or not. And so this is kind of,
so was it the case that the census data actually had the actual income, but the Ronnie and collaborators, they binarized it?
That's exactly right.
Interesting.
So the census data has the raw, income variable, in the numerical income variable, and it was binarized in a somewhat ad hoc way. And so there's actually a lot of information that was lost. And what is interesting, as a result of this choice, because the base rate, almost everyone is like below the threshold among the Black population and among women, the classifier accuracy, if you train on UCI adult, is actually higher for individuals in these groups, which is sort of the opposite of, one of the core fairness concerns, right? One of the narratives in fairness and machine learning is that, disadvantaged populations have, experience lower accuracy. Well, in this data set, it's actually quite the opposite, because, most of the instances are just no instance or below the threshold. The accuracy ends up being way higher. Okay, so here, once you reconstructed adult, we can change the threshold, right? We can vary the threshold, and that's what this plot is doing. So on the x-axis, we're varying the income binarization threshold from 0 to 70,000. And we're looking at the accuracy that you get with a gradient boosted decision tree model. And we're using that just simply because it gets roughly peak accuracy on this data set. It's one of those things. You have tabular data, usually boosted decision trees are pretty good. And so here you can see something very interesting, right? So of course, as you take a more extreme income threshold, like a baseline prediction, all yes or all no, gets better. And it has 50% accuracy when you hit the median, income level. But it's interesting to look at the subpopulations, the entire test set, the white population and the black population, and you'll see that there's actually a threshold or a crossover point, in the accuracies right around the median income. Okay, so this is this interesting, qualitative change where the groups have like a different relative ordering in terms of accuracy, right? And usually the typical narrative around fairness is more like to the left of the median income. So here the black population would have lower accuracy, or classifiers on the black population would have lower accuracy than for the white population, which is often what people assume is the case. Okay, so the crossover point is here at the median income level. Similar plot is true for men and women. The crossover is just around the median income. And you can actually see that the threshold that's in UCI Adult at 50,000 maximizes the difference between accuracies of men and women, okay? So, it's actually a pretty extreme threshold in that sense. So another thing that's interesting is that when you look at the value of different fairness criteria, and we'll get into the definition in a moment, but just think about having some measure of unfairness, right? And you vary the income threshold. You can imagine that also this measure of unfairness varies, okay? And so you can see here an example of 3 different fairness methods and how, they're just the value of the, measure of unfairness that they get vary significantly with the income threshold, okay? So they appear to be a lot more effective for some income thresholds than for others. And so you can see that it's relevant for the evaluation of fairness methods, which threshold you pick, okay? All right, so this raises the question, can we sort of get the best of census data while addressing the issues that we have with UCI Adult? And moreover, can we somehow get like a more diverse and more interesting set of benchmarks for fairness in machine learning research, okay? And so this is where our new data sets and findings come in. We created a package called folk tables. It's a new Python package that wraps around census data. It's available at folktables.org, and it gives you new prediction problems in domains including income, employment, health coverage, travel time to work, and mobility. So lots of different domains that are sort of available in census data. And you can use it as a plug-in replacement for UCI Adult if you want. So if you have code that already runs on UCI Adult, it'll be very easy to swap it out and plug in these things. But it's also easy to create other prediction problems that you might want to create based on census data. Okay, so it's not limited to these things. And one thing that's particularly interesting about this data source is that it gives you many states and many years. Okay, so it's available for like more than 20 years. We currently have 5 years in the release. There are 50 states. And so it's actually a great test case for studying performance variation and distribution shift, even outside fairness research. So if you're just interested in some other thing and how it varies by state and year, this is a good, data set to look at. All right. Why the name, by the way? So it's a name that we made up to describe tabular data about individuals. That's why it's called folk tables. And the idea is that sort of we want to emphasize that data has the power to create narratives about populations. And so we want to sort of challenge us to think carefully about the data that we collect. All right, so that's why the name is folk tables. It's pretty clever if you think about it. And you know, an unnamed assistant professor created this logo. Okay, so also proud of that. And again, it's very easy to install. I've used it in class this year. It's pretty convenient. You can just pip install it, and then there's like 3 lines of code to like get it to run, and you can get going. Okay, so this is just like an you know, snippet that shows you just how easy it is to pull the data and get going. All right, but more importantly, let me talk about the insights that we get from these new data sets and what they say about the state of fairness in machine learning research. Okay, so the first thing we see, or let me like take a step back. What we did is we kind of looked at these data sets. We took a first broad initial sweep of empirical findings from these data sets. And that's by no means exhaustive. So there's a lot more that you can do with these data sets. And I'll mention a bunch of open problems in the end. So basically, you know, the first thing we saw very clearly is that fairness criteria, the value of fairness, different fairness criteria, different measures of unfairness, as well as the effect size of algorithmic interventions vary greatly by state. Okay, so you have a lot of variance by state. And another thing we saw is that training on one state and testing on another state leads to fairly unpredictable results pretty consistently. So this is kind of interesting if you have a software tool that was developed in one state and then you want to ship it to another, it's not clear what you get. Third, fairness criteria appear to be more stable over time than predictive accuracy. So if we look at, you know, changes over time, the value of fairness criteria are actually pretty stable. They're pretty robust. And this is true even before or after you run algorithmic fairness interventions. We also noticed that increased data set size does not necessarily help in reducing observed disparities. So the disparities that you get in 1994 are very similar to disparities that you see in 2019. And so social progress as measured in years past is not necessarily like a, you know, something that will reduce these different measures of unfairness. Okay. And another interesting thing is that simple threshold adjustments, if you try to satisfy different fairness criteria just by adjusting thresholds in your decision rule, that typically outperforms more complicated fairness interventions. And I'll tell you toward the end why I think that's true. Finally, tools developed that were, tools that were developed for UCI Adult struggle with seemingly similar data sets. So it is actually a little bit concerning that, you know, the entire community used this one data set, because things don't necessarily transfer easily to other contexts. Okay, so these are the primary findings. I'm going to give you like a few, you know, slides and figures and plots about each of these, I think, and then we can discuss them a little bit more.
But, you might be going into this in more detail, but what kind of interventions are you thinking about in point 1?
Yeah, so in point 1, so it's, and in fact, I'll give you a bit more context on that in a moment. It's whenever somebody has like an algorithm for satisfying some kind of fairness criterion. Okay, so when I say algorithmic intervention, what I mean is somebody took a, you know, there's a paper which says we can satisfy fairness criteria in XYZ using this kind of method. Okay, does that make sense? For now, just take that as a sort of like an abstract statement, and I'll tell you what the fairness criteria are in just a second. So yeah, let me give you some context. As Nihar said, you know, what are we talking about here? And this is kind of like a 2-slide summary of like statistical fairness or statistical fairness criteria and this area of algorithmic fairness. And typically what you have as ingredients in your design space are features, target variable, a risk score, and sort of a status in a designated protected category, which could be sex or race or something like that. And then you try to design, you know, things that, or, you know, fairness criteria try to give different answers to the equality of what question. So basically, you're going to equalize some statistic based on these different variables, and different fairness criteria sort of track different normative understandings of what we should equalize. Okay, and the 3 most common criteria are demographic parity, where we equalize acceptance rate in all groups. So we want that our classifier has, an equal acceptance rates in all the different populations that we consider. Error rate parity is equal true or false positive rates in all groups. So this is saying we should have make an equal or proportional number of mistakes in each of the groups. And finally, calibration says that we should have equal positive outcome rates given a score value. So if you look at instances of a given score value in each group, they go on to be positive outcomes at a similar rate or at an equal rate. Okay, and so one thing that's sort of been or kind of occupied the community quite a bit is the fact that any two of these three are mutually exclusive in general. Okay, so there's a lot of like discussion and like study of like the different trade-offs between these criteria, and that you can't have all of them. Okay, so this is a bird's eye kind of summary or view of these different criteria, and there are I'd say at least three different ways to conceptualize what these things are actually trying to do. Okay, so the first one, you could think of these criteria saying, okay, look, these are kind of diagnostic tools to surface different moral hazards. Okay, we can evaluate these kind of definitions on data sets and see if the value is high. So use them as kind of a measure of unfairness. And then if the value is high, you might say, okay, this shows that a certain issue has occurred, or that there is a moral concern here that we want to investigate closer. So you can think of them as diagnostics, or you can think of these things as algorithmic interventions that act on as constraints on classifiers. Okay, so you could try to achieve these criteria either using pre-processing, let's say in the form of learning a fair representation, so kind of a feature representation that satisfies one of these definitions. You could do it in training with various regularizers or Lagrange multipliers and so on. Or you could do post-processing, which is you take a trained model and you adjust group-specific thresholds in the acceptance rule to satisfy these criteria. Okay. So, and actually, the third one is neither, and there's some robust debate around, do these things have value as either of these tools? Okay, so, but what I want to say is that many of the 300 papers, interpret fairness criteria as algorithmic interventions. Okay, so many of the papers that use UCI Adult use it as a test case for measuring how well some kind of method works as a way of achieving a certain fairness criterion. Okay. Nihar, does that address your question?
Yes, thank you.
All right, cool. Yeah. So so let's look at how fairness criteria differ widely by state, and this is something I found quite fascinating. If you simply look at error rates by state in different racial groups, here's what would happen. So in these scatter plots, you have false positive rate on the x-axis, true positive rate on the y-axis, and each blue dot is one state, and each red cross is the United States population. And as you can see, the trade-offs between true positive rate and false positive rate differ widely by state, especially as you get into smaller racial groups. They're all over the place. And so in fairness research, we have often this narrative that, well, oh, there's this sort of trade-off and we need to, consider how this trades off with some other thing. But actually, there's so much intra-population variance when we look at these fairness criteria that it's very slippery. It's a very slippery notion to even say, we have this kind of statistical trade-off, because it depends so much on the exact population that you look at. Okay, so the intra-population variance sort of outweighs other factors very easily. The other thing that we noticed is that intervention effect sizes vary across states pretty significantly. Here's a representative set of states, and each arrow shows you how the intervention, so the application of the algorithm, changes both accuracy and the measure of unfairness. And the measure of unfairness is just the difference in acceptance rate between two groups. And you can see that these arrows look very different in different states. They look different for different methods, obviously. You can see that for some pre-processing methods, we get only very slight improvement in fairness with a large drop in accuracy. And in some states, it's even a negative result. So we don't even get an improvement in all states. It could be worse in some states. And in other things, we get like a smaller trade-off, or a smaller change in accuracy and a larger change in our measure of unfairness. So basically, again, how we evaluate these criteria is very specific to the population we're interested in. And so when we talk about the performance of these methods, we ought to specify what population we're really talking about. And there is no such thing as like the accuracy of this tool or the error rate of this tool and so on. All right. The other thing that I found relevant is that transferring algorithmic interventions from one state to another may not work as expected. So here is an example of training on California and testing elsewhere. So you train a classifier on California data to enforce demographic parity, so equal acceptance rate. And then you evaluate the classifier in all 50 states. Okay, each dot corresponds to a state. And you look at the demographic parity violations across different states. And what I find interesting here is that imagine a software maker in the Bay Area is producing a tool based on data that they have and then selling it across the United States. I would say that this is kind of the picture that you get. Okay, so you would see widely different accuracy values across different populations, and also completely different, fairness criteria, or different values for the fairness criteria. Another interesting thing that I don't quite know exactly why it is that fairness criteria violations may be more stable over time than predictive accuracy. So if you look at different years in the data and you look at accuracy, then we have a typical decline that you would expect. So if you train a method in 2014 and then you evaluate 2015, 2016, 2017, 2018, and it goes down. But if you look at a measure of unfairness like demographic parity violation, it's actually completely stable over time. Okay, so even though the accuracy drops, violations of the fairness criterion remain stable. Okay, so let me draw some lessons of these that I hope will kind of inform discussions in algorithmic fairness and maybe also challenge some of the narratives. First of all, whenever we talk about algorithmic fairness, we need to understand that all these statistical criteria are extremely sensitive to population, okay? And we can't just say, oh, this is the accuracy of COMPAS, or this is the error rate disparity of COMPAS, like COMPAS is one of these criminal risk assessment tools. We need to, interrogate more closely what populations we're actually talking about, okay? There isn't a single accuracy number or a single trade-off. And intra-population variance can outweigh other factors. Second, risk assessment tools that are developed in one context may not transfer gracefully to another, okay? And we as computer scientists and machine learning people should actually challenge software makers along these lines. If somebody says, we developed this tool, our first question should be, well, on what population? And why do you think it'll work anywhere else, okay? And so the choice of the population is kind of a neglected normative issue in all of these discussions. And it shows up with like very concrete questions, like suppose we decide that we should train on a state-by-state basis. Why not county or city level, okay? If we think that the right answer is to train on the US population or the state or the county, how do we make these decisions? And how do we, figure out what the right thing is? And if we have any of these risk assessment tools, what is the training population and what is the test population? And so that kind of aspect is completely missing in a lot of the discussions.
Moritz, wouldn't it also be possibly the case that, so you're saying, okay, like you can't have demographic parity at a national level and then just, assume that it's going to hold within every state, but conversely, if you produce models like that separately achieve demographic parity in every state, like typical like kind of Simpsons type, just because the demographics change, there's no reason to believe you would have demographic parity at a national level, right?
Yeah, that's exactly right. Yes, and this is what we're seeing in these experiments. If you decide to train state by state, then you may not get it, at another level of, granularity, like the population or, jurisdiction, county, etc. Right? So I agree with you. It's one of those things where, of course, we can try to do, causal modeling to understand, how these things transfer and so on. But, again, we need to kind of have the conversation on like, how should we do it, right? But your point is exactly right. You wouldn't necessarily get it on the United States population. Although in this case, I think if you train state by state, let's see. Yeah, I think if you train state by state, we observe that it's not too different on the national level, at least. That makes sense. Yeah. Fourth, again, I think tabular data is a bit neglected, and it's underappreciated because I think a lot of bureaucratic decision making is happening on tabular data, and we're getting a little bit carried away with vision and image data and so on. But we shouldn't forget that the whole bureaucracy that's holding this sort of economy and country together is based on like plain old tables, right? And a bunch of the things we know from vision do not transfer. In particular, in these cases, you often don't have base error rates that are zero. Okay, it's not like a task that's realizable. You can't necessarily do it perfectly, but you get to the base error rate more quickly than for vision. Okay, so for a lot of these tabular data sets, it's not too hard to find a classifier that has base error, but the base error may not be zero. Okay, again, and I've said this many times in different ways, narratives are specific to population and method. Okay, so this is just something that we need to grapple with. So let me talk a little bit about the use and limitation of this package, right? What can you do with it? What shouldn't you do with it? First of all, stating the obvious, folk tables is not meant to replace substantive social research on census data. Okay, so it's the prediction tasks that we expose are not, meant to support social research on inequality or unemployment or housing, et cetera, right? I mean, there is established social science going on that does that directly from the census data, and it's not trying to change those processes. The intended use cases that we have in mind are more like performance comparisons and benchmarking within the community, within the machine learning community, to like figure out what these methods can do and can't do. And in particular, like illustrating limitations of different methods and surfacing questions like, state by state variance and so on. Okay. And I should say that decidedly, this is not limited to fairness research, and I'll give you some open problems, which are just outside of fairness research. And I think it just makes sense for distribution shift and transfer generally to use these data sources. However, unfortunately, like so far, this is very US centric, right? It's based on the US Census Bureau, and it contributes to the fact that research in machine learning is currently fairly US centric. Okay. Oh, there are a couple of questions that I missed. So Michael is asking, is one potential response here to the inability to generalize across states to use a definition of subgroup fairness, i.e. disadvantaged person by state of residence? I see, yeah. So you're saying, look, we could, make the location part of the geography that we're looking at. And then you get vastly more groups. And this is a little bit like enforcing the fairness criterion at the state level. Yeah, I think this would be interesting to see how that compares with training a separate model for each state. And then, using different models on each state, or like training one big model where you use that kind of fairness definition. I don't know what would happen, or that kind of group definition. Johan is asking, how long do you think these state-based will endure? These state-based will endure. How often should we update their content? what about data from other countries which could have very different demographic information? Yeah, so, okay, Johan, you anticipated, I think, what I was just saying about US-centric. So this is exactly right. It on its own doesn't, address that issue with machine learning research, but hold that thought, because the service that I mentioned, IPUMS, has, data from 102 countries. So we're hoping that someone will extend folk tables in that direction. I'm not sure I understand the question about endure. So maybe if you want to rephrase that or something, I can try to address it again. Sorry, that didn't quite get that. Okay, cool. So let me mention some research directions. If you're a grad student looking for, something to work on, I think these are quite worthwhile. The first one is that a conjecture that might seem technical at first, but I think it's actually quite interesting. I would conjecture that on tabular data, simple threshold adjustment is typically the optimal way to achieve, let's say, error rate parity, okay, and related fairness criteria. And so that means there is no need for like a very complicated intervention. Simply adjusting the thresholds will do as well as you can. And there's a theorem that we proved in this paper with Eric Price and Nati Srebro, which shows that this is true if you adjust from the base optimal predictor. So if you take the base optimal predictor and you do adjustment on top of the optimal predictor, you will actually get an optimal predictor satisfying the constraint. Okay, and so what we're saying basically here, or what this conjecture is saying, is that you would get this if you knew that you had the optimal predictor on these tabular data sets. And so what I find interesting about this is the question, do we get the optimal thing on these data sets or not, right? Like if you look at UCI Adult, do we get the base optimal predictor? I would say yes. I would say we can probably train like some large boosted decision tree or whatever and get pretty close to the optimal thing, but I don't know. So this is something I would like to find out empirically. And again, there's lots of views outside fairness research. For instance, I think that similar observations should actually apply to the causal inference literature. For instance, if you're asking, do causal effects transfer from state to state or from year to year and so on, the answer is probably that they're quite all over the place. And if you run different causal methods, you get very different estimates based on different states and so on. So I think there are a bunch of different ways that you could use these data sources in other domains to figure out similar things. Okay, so I think it's generally a good test case for studying distribution shift outside cognitive domains. And yeah, this goes back to the question that Johan asked. We'd love to see somebody extend folk tables to international census data, and it's available. Okay, so there's on the service that I mentioned, IPUMS, there's data from 102 countries available. So it's more like a question of integration. And I'm sure you would see all sorts of very interesting things. And you would see that, different countries, give you very different observations, and that it's not a good idea to only study the United States, right? And so I think this is definitely like a step I would find very worthwhile if somebody took it. I would love to support that and see additional countries represented in folk tables. All right, so these are just some directions. If you have questions on those, I'm happy to chat with you about that. And that's all of it. I want to mention, if you want to read more about data sets as benchmarks, of the history of it and how it came about and what it does and doesn't do, it's part of a new chapter on data sets in this book that I wrote with Benjamin Recht that is about to be released. All right, thank you.
Thank you, Moritz. Can give you a virtual round of applause.
Happy to take.
Cool. I think Johan have a follow-up question, like basically clarifying his or her.
Yeah. So Johan's saying whether these data sets could be invalid one day and we'll need to update them once in a while. Yeah, this is interesting, right? So what's kind of the life span of a data set, and how do we decide how long we want to keep them around, and based on what considerations? I think that's That's a really good question that comes up here, and I don't exactly know. Yeah, so that's a good point. Amanda, you have a question?
Yeah, Mandy, I can just unmute you.
Yeah. Yeah, hi, thanks for a really interesting talk. I particularly found some of the lessons you went through pretty fascinating. And I'm wondering like whether you think the key takeaway here should be the standard ML approach of comparing like our new method to like quote state of the art on a benchmark, if that's just kind of fundamentally like not suitable for algorithmic fairness, or if that process is kind of salvageable, but researchers just need to do a more kind of like comprehensive or nuanced empirical analysis on benchmark data sets.
Yeah, that's an excellent question. And I would say it depends on what you want to do, right? So I think, you know, what is probably not salvageable is that we use ML benchmarks to do sort of substantive work on criminal risk assessment or the criminal justice system and so on, and like extrapolate arguments about, you know, how things should go in these domains based on benchmark data sets. I think that's sort of something where we should apply established methodology from the social sciences and, you know, ask specific questions about the domain, right? What I think machine learning benchmarks can be useful for is, you know, for instance, you know, this observation about distribution shift, right, is politically very significant, right? Because right now, software tools are being advertised as having certain accuracy numbers, right? And it's for us machine learning people to say, look, actually, this is fictional, right? I mean, these, you know, software tools don't have just one accuracy number, and we know that they're not going to transfer gracefully to new populations. And here are our data sets showing that very clearly that these things don't transfer gracefully, right? So you could imagine using these data sets, these benchmark data sets, very effectively in certain political arguments about software tools, right? And so I think there is a place for machine learning benchmarks. We just need to recognize sort of what the limitations are of these things. And I think that on its own is like an interesting research direction of like, exactly where is the line between a machine learning benchmark and what a machine learning benchmark can do in this area and what it can't do. Right? And there is a paper by called "It's Complicated." I don't know if you've seen that, which goes into is related to this point of like what kind of data sets or what data sets can and can't do in this space, right? And so it's another paper I'd point to. Ivan has a question.
Yeah, thanks for a great talk. I have a question. I mean, it's a nice observation, right? That when you have a model trained on a national level, and then you look at this model within a state, you see some violations of the fairness measure. But did you try to like say randomly subsample examples and see? And I guess like if you have a model trained on a full data set and then you subsample large enough part at random, you'll still have some variation, right, in the fairness measure.
Yeah.
So would it be very different from the one you observe in actual states? And would it be kind of a measure of, you know, how meaningful the violation on the state level is?
Yeah, excellent question. So we did do that, and I'll go back to these slides a little bit. Let's look at this, for instance, right? These crosses that you see under the blue points are error bars, and they show you how much things would vary just by random fluctuation. And so they would tell you, you know, if you just randomly subsample data points, how much would these things move around? And you can see that some of them are in fact overlapping, right? So not all confidence intervals are non-overlapping, but there's definitely like a bunch of them that are non-overlapping. Like if you look at the accuracies close to 0.8 and the accuracies close to 0.7, those are all non-overlapping. So there are a bunch of points that are significantly different.
Right, but here it seems like that there's a significant difference in accuracy, right? But in terms of say demographic parity, it's kind of centered around 0, right?
Not all of them, but you're right that in this case, the the error bars for demographic parity are much bigger. But yeah, okay, it's actually kind of hard to see, but some of them are non-overlapping. But yeah, good point that this is the error bars are more overlapping for demographic parity for sure.
But say if you think of it from the, like, say, application standpoint, right? If we run some national program, right, where we need to make decisions, shouldn't, like, what is a dangerous outcome of only caring at this parity at the national level?
Yeah. Yeah, I mean, sort of the normative issue that I see here is like, look, suppose somebody trained a model on the national level, and now we're deploying it in, Harris County, Texas, right? And in Harris County, Texas, somehow the accuracy is terrible, right? And we could do much better if we had trained the tool on Harris County. Like, what sort of moral basis do you have to use the software tool that was trained on the population, right? I could easily see somebody making the argument, hey, it's very feasible for us to train this on local data. Why don't we, right? But then again, like, if we say, okay, now we have like moral backing to train locally, we get like different, trade-offs in different, you would have, you have run into other issues, right? First of all, may no longer have any guarantees at the national level, or it might be like a complicated mess, and we would have to like have all these data repositories where like every little county has their own like training pipeline and so on, right? So it might be simply like organizationally not feasible. And so I think this is the kind of issue that I see this running into, which I find very fascinating because I don't know how to resolve it. So.
Thank you.
Just as a quick follow-up, how much does this discrepancy compare with, let's say, if you trained within a state or within a county, you trained on one part, let's say one city or one borough, and then you try to predict the other. Like, is there much less variation there?
Sorry, you're suggesting you train on.
Right. So this plot is training on one state and then trying to run on a different state.
Right.
However, now let's restrict attention to a single state, let's say in California, and then let's say you train it on San Francisco,
Right.
but try to now run it on LA. Right. So is there much lesser variation at that level?
Good. This is interesting. I don't think we've looked at that systematically, right? So the data lets you go down to county. So you do have counties. You could go one step further down to county and see what happens there. At some point, some of these group conditionals will be pretty thin, right? So if you now condition on one of the 9 racial groups in a county, you might get very few points. And so even here, as Ivan observed, the reason why these error bars are huge for demographic parity are the small groups. And if you looked at the 2 largest groups or whatever, they'd be much smaller. The error bars would be much smaller. So yeah, I think you're going to run into the issue of like, just standard deviations being huge at that level. But I think you could probably still do it for some large counties and get an idea of that. And we haven't done that. That's
like curious. Like, suppose you could simulate the world multiple times, right? Then you could extend this argument to say, hey, you have a 99% accuracy at the population level, but then on myself, you have very, very low accuracy. So you, of course, could, tweak the model so it works well on myself. Right. So this is essentially infinite regress, right? I mean, to a point of a single data point, which can always complain about being classified inaccurately in a sense. Yeah. Yeah, there's this line of work by Michael Kim, Omar Rangel, Cynthia Dwork, and others on individual probabilities in this context, which kind of is following through on that. Like, what happens if we just, pursue that argument and talk about things like individual probabilities, right? What does it mean to make, predictions at an individual level, right? And I agree, there is this question of like, where should we draw the line, right? How do we choose how granular these things should be, right? And based on what arguments? That's a good point.
I think Zach also has a very long comment / question.
Zach, do you want to say it out loud, or you want me to read it?
Oh, sure. Just broadly, the insight that is you very from one population to another, models tend to not perform as well, or that, accuracy numbers calculated on one pop, whether it is as you vary measurement equipment or as you look across time, like this is something that has been a consistent observation in every single domain where we've looked for it. It's true when we look at models in medical contexts that are rolled out, over years. It's true when we look from one in NLP from like one NER data set to another. It's always the case that sort of the out of domain models, sort of almost always the case, I'd say, unless like there's some compensatory factor, like, in a deep learning context training on a massive data set versus a small in domain one or something. But in general, like, it's sort of broadly,
yeah, no, I know what you
like,
mean.
is that a novel finding, or insofar as that there's folks who are sort of making sort of in a context where it's irresponsible, like unqualified claims about accuracy, where what their intent is to deploy these models in different populations from where they're training it. Like, is the problem that they lack evidence, or is there something like a more fundamental kind of social or accountability problem, and no amount of evidence will address it?
Yeah, so I think, a couple of things, right? So first of all, not everything we're seeing is, there's some differences, like the fact that fairness interventions are more stable over time. That's something I didn't expect. I expect them to be around over time. So there are some things here that are different, which I would look at more closely. But the point stands that, of course, this is the issue with distribution shift, right? That it always, like, all models degrade. What's different here is the political environment in which this becomes relevant, right? And I think part of it is evidence creation, right? Like giving, stakeholders the evidence to contest some of these claims and, engage with people who are pushing for software tools in different contexts to concretely say, look, here is research showing that these things will behave erratically. So you better tell us, which population you trained this on and why you think it'll still work here, right? So I see this becoming relevant in comparisons of humans and machines, right? Where, you keep making like arguments of like, oh, humans are so inaccurate, we need to like deploy, statistical models here and so forth, right? So I think this is just tying into a different, conversation. And as a result, it has a different, or not necessarily the same, how should I say, conclusions or takeaways as you would have in like vision, deep learning, distribution shift, right? Cool.
Did you look a little bit closer, by the way, at that finding, that demographic parity? I guess you could imagine some kind of facile stories for why that would happen. Like if you had a fixed threshold and whatever, if all the scores went up or all the scores went down or something like this relative to, right?
Yeah.
You'd expect to see the demographic parity would be more or less conserved and accuracy would get worse. But like, did you see anything kind of, were there any simple explanations?
Yeah, I think that's a good hunch. I think, part of why this is probably true is that, income distribution has been, or the relative income distributions have been somewhat stagnant, right? And so the same adjustments still work, right? So in other words, the nature of the disparity hasn't changed much over the years. But I think this is why I was making this point that it matters, it matters that to observe that things don't necessarily change over time, right? And that we can't just hope that somehow these things will sort themselves out. But I think, what it means is just that the same thresholds work, right? And why do the same thresholds work? Because, well, the scores change, but like relatively, it's the same adjustment that's needed. That makes sense.
Right. And like, absolutely, the threshold could be getting worse. It's just that the threshold adjustment still works.
That's right. Yeah.
Yeah.
Cool. Are there any other questions, comments, feedbacks for Moritz?
All right.
All right. Yeah, I think we're also about to run out of time. So